Lesson 4 is differentiability and continuity. Gosh, can't talk here. So we are connecting them today. So connecting the differentiability and continuity and determining when the derivatives do and do not exist. We talked the other day about those, like for instance the sharp points, when derivatives do not exist. So coming back to some of that same stuff. So we're going to investigate the relationship between differentiability and continuity. Our focus will be to determine when a function fails to have a derivative. A function that is differentiable at a point is also locally linear at that point. So basically this is telling us in order for a function to be differentiable, the graph must be continuous and smooth. There's a good, we talked about the hard points. They're continuous, but they're not smooth. Remember when we say a function is differentiable, this means the derivative exists or you are able to take the derivative. So, differentiable, continuous, and smooth. And if it's differentiable, it means the derivative exists or you're able to take the derivative. So anytime we talk about differentiable, big word there. Okay, so our mathematical definition here. Differentiability at a point. A function y equals f of x is differentiable at the point x equals c if and only if, and what's the gist of this saying? It's the limit as x approaches c from the left is equal to L is equal to the limit as x approaches c from the right. Okay, so here we're looking at basically the limit from the left must meet the limit from the right. Am I correct in remembering that L just represents the limit? It just says where L is a finite value, so we can't, we can't have infinity here. But we're looking at limit from the left equals the limit from the right, and I'm pretty sure L is, I'm trying to remember what they used there. L representing the limit, if I recall correctly. Okay, so differentiability. Now, we've already talked about some of these, but how might f prime of a, when I say f prime of a, that is short for saying the derivative, yes? F prime, that's derivative, anytime you see that prime. So how might the derivative fail to exist? Following examples show us how a function will fail to have a derivative at a point where there is a corner, a cusp, a vertical tangent line, or a discontinuity. So all those things the other day when you guys were not happy with me, okay, or Aiden wasn't happy with me, at least I know, right? So let's look at some of these. Okay, so example 1, okay, based on what we talked about the other day, you know where this graph is going to fail to have a derivative, yes? At 1, because that is that hard point, okay? Now, let's work through, though, what they're talking about. Given the graph of f of x equals the absolute value of x minus 1. First of all, what is f prime of x as x approaches 1 from the left? So what am I asking for? I'm asking for the f prime of x. What's f prime of x? Derivative. What's the idea behind derivative? It's the slope of the tangent line. Okay, so what's the slope of the tangent line as x approaches 1 from the left? Basically, what's the slope of the line, right? Because it's already a straight line. So that slope is -1, correct? Okay. What is f prime of x? So what's the derivative, or the slope of the tangent line, as x approaches 1 from the right? What is this derivative over here? +1? Okay. Now, is f continuous at x equals 1? This is continuous, yes? I can draw this with one line. I don't have to pick up my pencil or anything. So yes, f is continuous. Is f differentiable at x equals 1? No. Are we able to take the derivative? Okay. And keep in mind, when we go back up here real quick, this is the limit as x approaches c, but what limit is this? This is the derivative, yes? So this is, does the derivative on the left equal the derivative on the right? And that's how we can, that's part of our definition here, is that the, f prime of c from the left, I don't think that's proper notation, and f prime of c from the right, those have to equal. The derivative on the left has to equal the derivative on the right. Right here, they don't equal. Okay? How I have it written in official notation is since the limit as x approaches 1 from the left of f prime of x does not equal the limit as x approaches 1 from the right of f prime of x. Okay, that's our reasoning there. There is no derivative. Okay. Now, I have it written in my notes. I'm not 100% sure why I have it written in my notes, other than kind of as an explanation tool, but real quick I'm going to do a slope graph real quick. Let me rephrase that. We're going to do a slope graph real quick. Okay? The point of interest there is my slope changes at 1, yes? To the right of 1, what is my slope, did we say? It's positive 1. So what that means is at positive to the right of 1, my slope is always 1. Positive 1. So it's always up above. To the left of 1, what is my slope? Negative 1. So now what I know is that slope is always down there. It looks a little funky, but that's my slope graph. Okay?
Could you just...
Oops, that's not. What'd you start to ask?
Could you just have a line that starts on the negative side and then goes to the positive side?
I don't understand.
Like what we did on that line. Yeah, like the straight line.
Like a diagonal line?
Yeah.
But, so, this is already a diagonal line right here. This represents the slopes. My slope at this point is 1, at this point is 1, at this point is 1, at this point, at all these points my slope is 1. This is the slope graph over here. And so my y values represent the slope. Every time to the right of 1, my slope is 1.
So
okay.
Could those be curved?
Not for this, they can't.
In a different scenario?
Possibly, yes. Okay. Now, and I don't know if you guys, one thing that we'll catch on to eventually is that when you look at a function and its derivative, a derivative is always a power lower. So like a straight line or an angled line like this, a slant line is x to the first. A horizontal line is just x to the 0 because it's just a number. Just like if you look back on those homework problems. a graph that looked like an x to the third graph? Well, its derivative is more like an x to the second. So there is also that connection that might help too. Okay. And I guess it's, at the x value of 2, what is the slope? It's 1. So here at 2, slope 1. The x value of 5, what is the slope? 5, 1. You go over here at negative 2. The slope at negative 2 is negative 1. So negative 2, negative 1. Like you're just kind of turning them into points. Okay. 2 asks us, given this graph, which this is the cube root of x graph. So you guys know x cubed, right? X cubed is the vertical graph. The cube root of x, I think we looked at this a little bit last year in pre-calc maybe. I'm not sure. But it is the sideways version of x cubed. Use the alternate form of the derivatives, they give us the limit there, to show that the function has a vertical tangent line at x equals 0. Okay, so let's do our limit. The limit as x approaches c. What are we using for our c here? What's our value of interest? 0, yes? So as x approaches 0 of f of x, what was given as f of x? Cube root of x minus f of c, which in this case is going to be f of 0. What's f of 0? It's the cube root of 0 all over x minus c, which is x minus 0. Okay, clean this up. The limit as x approaches 0. What do we have on top?
X minus 0.
Okay, cube root of x is cube root of x. The cube root of 0 is 0. What's another way to express the cube root of x? It's x to what power? X to the 1/3. So I'm going to write this as x to the 1/3 on top. I have a way, I have a reason. On bottom, x minus 0 is x. Okay, clean this up one more time. What is x to the 1/3 over x?
X to the 1/2.
Check your math.
X to
How do we divide x's when there's powers involved? You subtract. So we're going to subtract 1/3 minus 1. Negative 2/3. So it's x to the negative 2/3, which is what in fraction form? How do you get rid of the negative exponent?
one on top.
Okay, you take it to the denominator. Said some very interesting ways there, but okay, it becomes 1 over x to the 2/3, yes? Are you with me? What happens is you try and take the limit here. Yeah. You have 1 on top, 0 to the 2/3 is going to be 0. And 1 divided by 0? We can't do it, can we? Okay. Our job was to show that the function has a vertical tangent line. We've done that by showing the 1 over 0 and showing that this limit is undefined. Okay. So I'm going to use my 3 dots and say, therefore, the limit is undefined. So we're showing that limit does not exist, it's undefined, and thus there's a vertical tangent line. Okay? Because if you do the slope of a vertical line, you're going to get something like 1 over 0, aren't you? Okay. Questions there before we turn the page? Okay, so example 1 had a hard point. Example 2 has a vertical tangent line. Okay. Example 3. Given the graph of f of x equals 1 over x plus 2 quantity squared, describe the derivative of f as x approaches -2 from the left and the right. So, I'm trying to remember how, I always forget how I write this part of my notes. What do we know as x approaches -2 from the left? What's the, okay, it's going to, oh wait, I almost messed this up. Notice it's the derivative of f. Okay, so as x approaches -2 from the left, I agree f approaches positive infinity, but we're being asked about the derivative. Well, first of all, what kind of derivative is this here?
Positive.
It is positive. And what's happening? The slope of this line is getting steeper. Okay, and steeper is a bigger slope. So this is f prime of x is approaching positive infinity on the right. So that's the derivative on the left. And now what are we going to do? As x approaches -2 from the right, I want to talk about the derivative. So now we're on the right here. As we approach 2 from the right, what is my slope doing? First of all, what kind of slope is over here on the right? These are negative slopes, yes? As we approach here, it's getting steeper and steeper and steeper again, yes? But steeper and steeper and steeper in the negative sense, which means what are we approaching? Negative infinity. Okay?
You lost me there. How?
Okay, so steeper and steeper slope. So say the slope is 1, the slope is 2, the slope is 3, the slope is 5, the slope is 10. But these are negative slopes. So, right, like we're going from the right, but you have to remember slope, these are all negative slopes. Does that make sense? Okay, so what did we just show here? The derivative from the left and the derivative from the right are not equal. So this, therefore, I'm going to use those therefore, this is not differentiable at x equals -2. Okay, now B, we're going to do this a slightly different way. This time, given the derivative, f prime of x, so they're giving us the equation of the derivative, use the formula to evaluate the derivative when x equals -2. So we just kind of tried to talk through it on the graph. Now it's going to be using the equation. So we're going to do f prime. We're going to plug in -2, but we have to use the left and the right. So I don't know if that's really correct, notation. But first of all, we're going to look at the derivative of -2, but from the left. Which means when I plug in, I'm not going to plug in -2. What can I use to the left of -2? What can we? A number close to -2 on the left. So I guess I heard -3. I want closer,
2.1.
like the -2.1. So I'm going to use -2.1 plus 2 to the third. Okay, it's -2 on top. -2.1 plus 2 is going to be -0.1, and then it's cubed. So when we do -0.1 cubed, first of all, what is a negative when you cube it? Still negative, right? 3 negatives is going to be a negative. 0.1 when I cube it. Well, 1 times 1 times 1 is 1. How many numbers after the decimal? 3. So 0.001. Well, here's the deal, folks. What? Well, a negative divided by a negative is a positive, yes? I'm trying to think how I wrote this. So it is going to be a negative divided by a negative. But what do you have? You have a number on top divided by a number that is getting smaller and smaller and smaller. The smaller this number gets, what's it do to the top number? Or the number in general, it's going to push it bigger. And so what is this trending towards? Positive infinity. And again, that whole infinity thing is because it's a larger number divided by a number that's getting smaller and smaller and smaller. It's always going to be infinity. Now, let's repeat the process from the other side. The derivative evaluated as we approach -2 from the right. So as we approach -2 from the right, what can we plug in this time? -1.9. And not that you can't go closer, but 1 decimal does the job. We see it. So -2 divided by this time it's going to be positive 0.1 to the third. -2 divided by 0.0001. Well, this time we have a negative divided by a positive. And what's happening? You've got 2, which is a larger number in reference to these very small decimals, but a set number, divided by a decimal that's getting smaller and smaller and smaller. So this time we're trending towards negative infinity. Okay. Did I again just show the limit from the left and the limit from the right are not the same? Okay, the limit of the derivative. Okay, the derivative on the left and the derivative on the right are the same. So, either way, what we know is that the derivative at -2 does not exist. Derivative at -2 does not exist because the limit of the derivative on the left does not equal Derivative on the left does not equal the derivative on the right. Okay? I guess you could say, what? F prime of negative 2, so derivative of negative 2 on the left, does not equal the derivative of negative 2 on the right. I mean, that's what we're saying. Okay. So that was your third way. In this case, we had a vertical asymptote. Okay? Okay, big idea on the next box. This one's huge. This one we use a lot. It's important. Differentiability implies continuity. If a function is differentiable at a point, then the function is also continuous at the point. So if you can show that something is differentiable, then we know for a fact it is continuous. Okay, so if f is differentiable, then f is continuous at that point. Differentiability implies continuity. That's a big idea. So they have this broken into two pieces. One, if a function is differentiable at x equals c, then it is continuous. Differentiability implies continuity. So all I'm going to say, if I say it's differentiable, you can be like, oh, it's continuous. You know, where we've been looking for things, what do we do? IVT, intermediate value theorem. In order to use IVT, we had to be able to show or know that the function was continuous. Well, if it says the function is differentiable, then you automatically know it's continuous. On the flip side of that, continuity does not imply differentiability. So if I say, oh, it's continuous, you do not get to say, oh, so it's differentiable? No. So it works one way, but not the other way. And this one has to do with sharp corners, cusp, vertical tangent lines, discontinuities. Just look at those like sharp corners and cusp. They can still be continuous, but that doesn't mean it's differentiable. Now, okay, I think he did this back in geometry. Do you remember writing contrapositives? One person at least does. Okay? I always struggle with remembering what's what. When we had the Saxon books for calculus, they had a section where we had to review like converse, inverse, contrapositive, and I feel like there was a fourth one. So I kind of wish I had that back because it was good for me. So contrapositive is what they want us to write. If a function is differentiable at x equals c, then the function is continuous at x equals c. Do you remember what it means to write the contrapositive? So, no? There's two things that need to happen. You flip the pieces and you also negate the pieces. Is negate the right word? Make them negative. So right now it says if a function is differentiable, then it is continuous. So flip the pieces, put continuous first, differentiable second. And right now it's saying if they are, now we're going to say if they are not. So if the function is not continuous, then the function is not differentiable. If a function is not continuous at x equals c, then the function is not differentiable at x equals c. Okay. Okay, you ready for example 4? Describe the x values at which the function g of x equals the absolute value of x squared minus 5 is differentiable. Justify your answer. So we want to know where this is differentiable. How do you want to describe where it is differentiable? You want to start out by telling me where it's not differentiable? Where is this graph not differentiable? That negative 2 point something and that positive 2 point something, right? Now, officially, that negative 2 point something and positive 2 point something, do you see this expression x squared minus 5 up here? Well, if you set x squared minus 5 equal to 0, this would be like finding x-intercepts because we're making the function y equals 0. Well, x squared equals 5, and what's x? Plus or minus the square root of 5. The square root of 5 is 2 point something. I don't remember what offhand. Okay. So, that is positive square root of 5 and negative square root of 5 is where it's not differentiable. So where is it differentiable? Think interval notation. What?
Negative square root of 5 less than
Think interval notation instead of inequalities.
negative 50.
Are we seeing it? So from negative infinity to negative square root of 5. My graph is differentiable, yes? Because that's this piece, the left piece of the W, if you will. What do I use on negative square root of 5? Parentheses, because it's not differentiable there, right? Now I'm going to use the U for union. What's the next interval where it's differentiable?
Negative square root.
Yeah. I think you guys are with me now? Yeah. Negative square root of 5 to positive square root of 5. Obviously both using parentheses, union. Where else is it differentiable? Square root of 5 to positive infinity. So that right there is describe the x values where it is differentiable. Now, justify your answer. Why is it not differentiable at those two places?
Because they don't equal each other on the side.
Okay. The
Derivative on the left.
Officially, yeah, the derivative from the left would not equal the derivative from the right, yes?
Yes.
The other thing you can use, what kind of points are these? Yeah. I have it written down as sharp corner or cusp, hard point, you know. So I have it kind of unofficial there, really, but since g of x has sharp corners or cusp at x equals, I'm going to say plus or minus the square root of 5. Okay? Okay. And so we pick up tomorrow?
Yep.
Tomorrow we'll go into more the official justification where we're showing the limit of the, or the derivative on the left does not equal the derivative on the right.